Okay guys, so what we're going to be doing today is we're going to start talking about a slightly different way to use all of the things that we have learned. Slightly different way to talk about like derivatives and things like that. And the first topic that we're going to talk about is optimization. Now in order to understand exactly what optimization is, what we have to do is we have to look at the project that we did from yesterday. And if you weren't in class yesterday, basically I gave you a paper that originally it was a rectangular piece of paper and it was 17 inches, by 11 inches. And we cut corners out of all four squares out of all four corners of the paper. And then we made a box out of that particular piece of paper. Okay. And hopefully you did that. Hopefully it makes sense. Okay. So when we look, what happened after that is we had like a three-dimensional box. So looks like this. There's my box. We folded it up. Most of you guys know what it looked like because you made it. Okay, so there's my box right there. Box, box, box. There we go. Box is looking good. So there's my box right there. I look at that and I'm like, okay, that is what my box is going to look like. Now you'll notice that you could call that shape like an open box, or we could call it a rectangular prism. And what we were doing is we were saying, okay, the dimensions of this, I guess we could say, originally we had a length, a width, and a height on this box. Now, what we were really doing when we cut those corners out of the box is we were changing what the height of the box would be. So if I don't know what the height is, because everybody's height was different depending on what box you created, then we would say that that is a variable. It's something that's changing depending on what we wanted to make it. And what we're going to call a variable in this particular example, you can call it whatever you want, but let's call it x. So I'm going to say that out of all of these corners, I cut out an x out of every single corner. Okay? So I look at this, if I want to look at it in this way, I could say that the height of this box is x. And then here's how we have to think about the other ones, okay? The volume of the box in general is equal to the length times the width times the height. That's how we find any type of volume of these rectangular prisms. So in this example, what we could say is regardless of how big or small we made our squares initially, I could say that this side is 17 inches minus each of the x's that I cut off of either side. So that'd be 17 minus 2x. And the same thing would be true for the other side when we folded it up, 11 minus 2x. So we could say that the length here is 17 minus 2x, and then the width here is 11 minus 2x. So I've got 17 minus 2x, I got 11 minus 2x. Those are my two different measurements for those different sides of my box. So what I could really say here is I could say that the volume, if we wanted like a formula to help us find the volume that wasn't like length times width times height, I could say that the formula is 17 minus 2x times 11 minus 2x, and then the height of the box would just be x. And whatever we decided our height was going to be, we'd just plug that in for x in this equation, and it would tell me what the volume is. So now we have ourselves a volume equation, okay? So if we were to multiply that out, and I'm just going to do this in the interest of time, I would FOIL that out, and then I would multiply the x in. When I do that, I would get 187x minus 56x squared plus 4x to the third. That would be my volume, okay? Now, if you recall, what we were trying to do is make this box hold the most amount of water. The maximum volume is what we wanted it to have. Well, another way we could say that is we are trying to maximize this, and that is exactly the same thing that we were doing when we were doing graphical analysis. We were looking to find maxes and mins by taking the first derivative of whatever function it is we're looking at. So in this case, if I were to take the derivative of my volume equation, it would be 187 minus 112x plus 12x squared. That would be the equation of the derivative of my volume. Now the reason why we would want to take the derivative of the volume is we would want to find out where a possibility for a max would be. And that would be by finding a critical point. If you remember, the way that we find a critical point is we take our first derivative and we set it equal to 0. So in this case, and this is the only case because I wanted us to look at this as more of a real life scenario, but when I look at this, what I have is I've got this equation, and there's no way to factor this equation down. So we would actually have to use the quadratic formula in order for us to solve this equation. So in this case, my quadratic formula, I would put it in, and I would get two separate answers. I'm just going to tell you what those are, because we don't have to know how to use the quadratic formula. But the two different answers I would get are 7.15 and 2.18. Now I have two different answers. These are my two different possibilities for me to have a maximum volume when the height of my box is one of these numbers. So it's either 7.15 or it's 2.18. Well, if you think about it, on my paper, only one of those answers makes sense. If I were to cut out a square that was 7.15 by 7.15 on this side, there wouldn't be enough length left to cut out a second side that was 7.15 in length as well. So if there's only one 7.15 length, that answer doesn't work. So I know automatically that what I would want to do, the sides of my square that I should have used in this particular example, were about 2.18 inches is what we were looking at in this case. All right. So that would be how big we wanted to make the squares. What we've done here, and I'm skipping past all of these things because we've already talked about those. What we did here is we did what is known as optimizing something. Okay? When we optimize something, that means that we are trying to get a particular length or a measurement to be as large or as small as possible. Sometimes it is as small as possible. So we're trying to get the most out of something, and we have to figure out all of the equations that go with it. The reason why people struggle with optimization so much is because you are very rarely just given an equation and say, hey, just take the derivative, set it equal to 0, and solve it. Instead, what we have to do is we have to come up with all of this information on our own. That's why these people struggle with these problems so much. You'll be given a scenario with no equation whatsoever, and you are expected to try and figure out what the answer is going to be to a situation without being given an equation. Okay? So we already talked about this stuff, blah, 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 blah. Okay, so there are steps that we should take when we do an optimization problem. Okay? Step number 1 every single time is you should draw a picture of what is happening in the problem and label everything. And these are not complicated pictures that you're going to have to draw. Most of them will be rectangles. Some of them will be triangles. Some of them are simple three-dimensional shapes. None of them are super hard, but you need to label everything. Okay? This is all the steps we do. This one's probably not the one that I would say is vital, but it is very important so you can visualize what is happening. Okay? So we should really do this so we can know what the problem's asking us to do. Now, step 2 is by far the most important of all of the steps that we have in these problems. The reason why I say that is because this is where, number 1, if you can do this step, the rest of the problem's actually pretty easy. And number 2, this is where we get our equation that we're going to actually take the derivative of. Now, you'll notice it does say that there are equations. Okay, there's more than one in every one of these problems that you have to come up with. So the first equation that we are going to look at is the equation of whatever it is that we are trying to optimize. Whatever it is we want to find the max or the min of, we need to come up with an equation for that particular problem. In general, this problem only has variables, and if it has constant numbers, they're numbers that were not given to us in the problem. And we'll talk about that a little bit more in just a second. But this is what we are trying to take the derivative of, this particular equation. So that's the first equation we have to come up with. The second equation that we need to come up with is what is known as it's supposed to say constraint equation, not restraint equation, so that should say constraint. It's the constraint equation. The constraint equation is simply the equation that when we look at it, it's whatever is given to us in the problem, we write an equation that relates to that. Okay, and this usually does have a number value in it. You'll have to include that number value in the equation. Before you move on, you have to have both of these equations. And really, this is the part that most people struggle with, because you'll look at it and you'll be like, I don't know what these equations are supposed to be because they don't give them to me. It's one of the reasons why reading the entire problem is so difficult every single time. Okay? Now, what you're going to do once you have those two, and we're going to do an example here in just a second where we will apply all of these steps, but what you're going to do once you have both of these equations is you are going to choose a variable in your constraint equation and then use substitution to plug it into the other equation. The reason for that is most of our optimized equations, the ones that we're trying to maximize or minimize, have more than two variables. They have 3 variables or 4 variables, and although there are methods that exist to take the derivative of those particular types of equations, we don't know how to do that yet. And so what we're trying to do is minimize the number of different variables that exist in our equation that we are trying to optimize, okay? And so once we do that, and again, this will make more sense when we do an example here in just a second, but once we do that, we're going to take the derivative of this new equation that we've just come up with, we're going to set it equal to 0, and we are going to solve that particular equation, okay? So now once we have this equation, you take the derivative of this new function that you have and set it equal to 0 to solve. We're back to doing calculus again. Technically what we would do is we'd find our critical values and we would make a number line, although honestly, almost every one of these problems we do, one answer just makes sense if we have more than one, and one answer does not, okay? So step number 5 is once we find those answers, we have to analyze the answers and make sure they make sense in whatever is going on in the problem. In other words, we should say what answer makes sense, and should that be the answer. Like I said, a lot of times we can just get rid of some answers. So here is another example. Okay, we've got a rectangular plot of farmland. Will be bounded on one side by a river, and on the other 3 sides by a single-strand electric fence. So I'm going to draw this picture immediately. So here's my river right there, okay? And then I've got a single-strand electric fence going around the river. That is all the information I have about the setup of this problem, okay? Then it says, with 800 meters of wire at your disposal, what is the largest area you can enclose, and what are its dimensions? In other words, I don't know how big to make the fence. Well, if I don't know how big to make the fence, that means I don't know how long it needs to be or how tall it needs to be. So we're going to call those variables because those are unknown. So I'm going to say this side is going to be X. Maybe we'll call this side Y. And then the side down on the bottom is going to have the same length as the top one because it's a rectangular plot. And we're not going to put a fence where the river is because the river is already doing a good job of bounding it on that one side to keep the animals in. Okay? So now I've got my picture. I've labeled it as best I could. That is step number 1. Now, step number 2, we've got to come up with our 2 equations. The first equation is going to be our optimization equation. What is it that we are trying to optimize? So in this case, I want to know what the largest area that I can enclose is. That's what I'm trying to maximize, is the area. Oops, I forgot I spelled optimize. Okay, so the area in this case, in my problem, based on the picture that I've labeled, is going to be X times Y. Now again, you'll notice I have 3 variables in this problem. I can't take the derivative of that yet because I've got too many variables. So I have to come up with my constraint equation as well. My constraint equation, notice it says I have 800 meters of wire that I'm going to use. And I'm going to use all of it, okay? So really, if you think about that, that means I'm going to start up here in the corner and just trail that wire all the way around. So I could say that my 800 meters of wire is going to go to 2 of the X's and a Y. So the constraint is going to be 800 equals 2X plus Y. That has to be true. I'm not going to waste any wire building this fence. So now what I do, I've got step number 2 done. I've got my 2 equations. That's usually the most difficult. Step number 3 is I need to decide what letter, and it doesn't matter, but we need to decide what letter in the constraint equation we want to get by itself. In this case, it looks to me like the Y is much, much easier to get by itself. So I'm going to have 800, minus 2X, minus the 2X over the other side, equals Y. So I take that, and that Y I substitute in to my area formula. The reason why I do that, you'll notice now my area formula only has 1 variable on each side, and I can go about taking the derivative and setting it equal to 0. So I'm going to have, what I'm going to do to make it a little bit easier to take that derivative is multiply the X in first, because I'm going to have to set it equal to 0, which means I'm going to have to solve it. So I don't want to have to use the product rule if I can help it. Okay, so I'm going to get 800X minus 2X squared. Now I want to maximize this area, so I'm just going to take the derivative of that, 800 minus 4x, and I'm going to set that equal to 0. When I do that, I get negative 4x equals negative 800. So x in this case, if I divide by negative 4, I get that x equals 200. So what that's saying is, in this case, if I want to maximize the area, both of these sides now need to have a length of 200. Well, if those have a length of 200, I know that y is equal to whatever 800 minus 2 times my x value is going to be. So 2 times 200 is 400, so I get y equals 400. So this is 400 meters over here. So that's what my dimensions are going to be, and then if I wanted to find that area, I would just take 200 and multiply it by 400, and that would give me 80,000 square meters. Which seems like a lot, but it's not like super huge. Whoops, come on. Oh. Okay. So, in this case, we would have 80,000 square meters. So this is an example of how we go about doing these optimization problems. Now, I'm going to let you know, because we're not going to do the next one, but instead I'm going to let you know you will struggle with these at first. It's very difficult when somebody's not kind of helping you, especially with step number 2. So if you're having a hard time, please, please, please come on in and get some help on how to set these equations up. Because once you get the equations, it's usually not awful. But getting those equations is very difficult. If you have any other questions as well, please come on in and I'm more than willing to help. Thanks.